Hello everyone, I'm Bill Stubbs, and this is the first in a series of videos I call Dissecting the Standard Model of Particle Physics, discussing the findings in my book, Three Quarks Missed the Mark, or The Neutron is Not a Dud, but the Standard Model is. The title of the book is a play on a line from James Joyce's Finnegan's Wake, Three Quarks for Muster Mark, often mentioned as where Murray Gell-Mann got the name for the particle from whenever quarks are introduced. As the title suggests, I present a case claiming to demonstrate that the proton is not made of three never-seen quarks, but of a collection of other particles routinely observed in nature. The subtitle, The Neutron is Not a Dud, is also a wordplay. In the Standard Model, the neutron is made of an up quark U and two down quarks D and D, making one way to depict it DUD or dud. My analysis will show that, like the proton, the neutron is also made of particles routinely observed in nature, not quarks. Finally, as the phrase, "but the standard model is," implies, I will show that most of the particles making up the standard model are not fundamental, and some don't even exist. Bad jokes and all, I self-published the book in November 2019, and you can get a copy at Amazon.com. In this book, I look at the experiments, analyses, assumptions, and conjecture that led to the formation of the current standard model of particle physics to try to gain insight into the choices made for the particles that make it up. In many instances, I offer alternative interpretations of experimental data that challenge the conclusions drawn from the original analyses of that data. In doing so, I realize that I am challenging well-established beliefs about the nature and structure of matter that many people will not be willing to give up easily. However, I do believe that my analyses of the data collected to date have strong bases and present as plausible interpretations of the data, if not more so, as the original work. I've had the luxury of examining the whole body of data at once rather than as it evolved over time. This allowed me to see patterns and trends that may not have been accessible to the original researchers at the time they were formulating the components of the model. I welcome comments, observations, suggestions, criticisms, etc. I just ask that they be constructive and respectful. Okay, let's get started. I'll begin by briefly considering the quest to determine the fundamental particles that make up the universe. It is likely, once people had time enough to think about their surroundings, they wondered what things were made of. As early as the 5th century BC, the philosopher Democritus proposed things were made of indivisible parts he called atomos, which today we call atoms. And while over the next 2,000 years, other philosophers, most notably Aristotle, challenged atoms, offering alternatives such as everything being made of earth, water, air, and fire, atoms prevailed. By the 17th century, Robert Boyle was using them to explain the behavior of gases. In the 1800s, John Dalton used atoms to develop a theory of matter in which he modeled many substances as various groupings of atoms. And in 1871, Dmitri Mendeleev devised the first periodic table of elements, arranging atoms by their recurring chemical properties. Prior to the 20th century, as Democritus proposed, atoms were thought to be fundamental particles, the smallest pieces of material one could get. But in 1897, J.J. Thomson found that negatively charged particles, eventually called electrons, could be knocked out of atoms, revealing that atoms were made of even smaller particles. In 1911, Ernest Rutherford showed that atoms also have a massive nucleus in addition to and independent of their electrons, and in 1919 that nucleus contained particles, eventually called protons, about 1,800 times the mass of the electron, with a charge equal to that of the electron, but positive. It was further determined that the mass of the nucleus in proton masses was about twice the charge of the nucleus in proton charges. With that realization, The nucleus was thought to also contain electrons that acted to cancel some of the charge of the protons, creating the observed mass-charge imbalance of the protons in the nucleus. The electrons in the nucleus were believed needed to hold the positively charged protons together in the nucleus by way of the Coulomb attraction between the oppositely charged particles. This, even though particles the size of electrons confined inside the nucleus violated the uncertainty principle. In 1932, James Chadwick determined that neutral particles about the size of protons, he called neutrons, were also contained in the nucleus of the atom, along with protons. With this discovery, electrons were removed from the nucleus in favor of neutrons, resolving the proton mass-charge ratio problem and the electron uncertainty principle dilemma. Now, after over 2,000 years as the reigning fundamental particle, in little more than 30 years, the atom had been replaced by electrons, protons, and neutrons as fundamental. Starting in the 1930s, several new particles smaller than atoms other than electrons, protons, and neutrons were found. In 1933, Carl Anderson discovered the positron, a positively charged version of the electron. Seth Nettermeyer led a group in 1937 that discovered the muon, often called a heavy electron. In 1947, Cecil Powell and Company discovered the pion, while George Rochester and Clifford Butler found the kaon. The electron neutrino was discovered in 1956 by Clyde Cowan and Frederick Raines, and the muon neutrino discovered in 1962 by Leon Lederman, Melvin Schwartz, and Jack Steinberger. In the early 1960s, these discoveries led several physicists, including Murray Gell-Mann, to show that particles thought to be fundamental, like protons and neutrons, could actually be characterized as collections of smaller particles he called quarks. Though dismissed as mathematical conjecture at the time, by 1969, a team of scientists using a particle accelerator at Stanford University revealed that protons and neutrons were, indeed, made of small charged particles. These particles were eventually declared to be the quarks Gell-Mann had proposed. With all the new particles found came a desire to determine those that were fundamental and classify them much like Mendeleev did for elements with the periodic table. In the mid-1970s, physicists dubbed this effort the Standard Model of Particle Physics. The current Standard Model consists of 17 particles divided into two families called fermions and bosons, which are thought to be the fundamental particles making up the matter in the universe. There are 12 fermions, which are the mass generators in the universe. 6 of them are Gell-Mann's quarks and are named up or U, down or D, charmed or C, strange or S, top or T, and bottom or B. The other 6, called leptons, are the electron, the muon, the tau, and their respective neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. All the fermions except the 3 neutrinos are charged, and each charged fermion has an antiparticle having the same mass but opposite charge of the particle. The antiparticles of the chargeless neutrinos have opposite helicities or handedness of the particles. The bosons are force-carrying particles. They include 4 vector or gauge bosons, the gluon, the photon, the W particle, and the Z particle, and 1 scalar boson, the Higgs. The gluon, photon, and Z particle are chargeless, but there is a W plus and a W minus. In the Standard Model, combinations of quarks held together by gluons form 2 classes of particles, baryons and mesons. Baryons are made of 3 quarks. For example, the proton is made of 2 up quarks and 1 down quark, the neutron 2 down quarks and an up quark, and the lambda 0 an up quark, a down quark, and a strange quark. While mesons are made of 2 quarks, more specifically a quark and an antiquark. For example, the positive pion is an up quark and an anti-down quark, and the positive kaon is an up quark and an anti-strange quark. Saying that baryons are made of 3 quarks is a bit misleading. The 3 quarks referred to in the Standard Model, often called valence quarks, are the only ones in the baryon that do not have an antiquark mate. According to the Standard Model, there are many virtual quark-antiquark pairs, called C-quarks, residing in the baryon at any given time, along with the valence quarks. The valence quarks give the baryon its identity, sort of like its fingerprint. The only stable baryon is the proton, with the next longest lived being the neutron, with a lifetime of about 15 minutes. All other baryons have lifetimes of less than 1/1,000,000th of a second. The table showing gives information on some of the more common baryons. According to the Standard Model, the unstable baryons decay into other baryons and usually a meson, the other quark-bearing particle. 2 exceptions to this are the sigma 0 particle, which decays by emitting a photon to become a lambda 0, and the neutron, which emits 2 leptons, the electron and its antineutrino, in becoming a proton. Seemingly all unstable baryons eventually decay into a proton, or a neutron, which also decays into a proton. In most instances, a pion is emitted when the baryon decays, but occasionally a kaon is emitted. The kaons quickly decay into charged pions, which decay into muons, or sometimes directly into muons, and other times into neutral pions that decay into photons. The muons decay into electrons and neutrinos. We'll take a closer look at baryons and mesons in a later video. The Standard Model offers 2 avenues for baryons to decay, one involving the strong interaction and the other the weak interaction. The strong interaction is the more prevalent one, emitting a gluon to produce another baryon and a meson as decay products, for example the delta 0 decaying into a proton and a negative pion shown. When a gluon is emitted, strangeness, a quantum property of fermions, is conserved. In the Standard Model, the strangeness number of a fermion is determined by the number of strange and anti-strange quarks it contains. Each strange quark a fermion has adds -1 to its strangeness number. For example, a fermion containing 1 strange quark has a strangeness number of S equals -1. One with 2 strange quarks, a strangeness number of S equals -2, and the omega minus particle, the only fermion made of 3 strange quarks, has a strangeness number of S equals -3. Anti-strange quarks, usually found in mesons, adds +1 toward the strangeness number. For example, the positive kaon, containing 1 anti-strange quark, has a strangeness number of S equals +1. In the Standard Model, the emission of a gluon by a quark cannot change the strangeness number of the resulting quark. Only the weak interaction can change a quark's strangeness. The weak interaction occurs when a quark in a fermion decays by W boson emission. When a quark emits a W boson, its charge flips. The negative quarks D, S, and B emit a W-, increasing their charge by 1 from -1/3 to +2/3, changing them into a positive quark, either a U, C, or T quark. The positive quarks, U, C, and T, emit a W+, reducing their charge by 1 from +2/3 to -1/3, changing them into a negative quark, either a D, S, or B quark. Once emitted by the quark, the W boson can decay into either a quark and an antiquark, or into a like-charged lepton and its antineutrino. Though the quark hypothesis has been crafted into a very efficient scheme for modeling and predicting fermion behavior, the fact still remains that no quarks or particles with fractional charges have ever been observed. In the next video, we will look at how the particles found inside the proton came to be considered Gell-Mann's quarks.